Welcome back to our heat transfer class, where we're delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of Energy. Remember that the introduction to heat transfer is divided into several lessons. In this third lesson, we delve deep into the world of heat transfer, where we will explore its real-world applications. Its goal is to explain to you in which applications engineers use the principles and equations of heat transfer.
Let's start by talking about the typical problems that can be solved using the heat transfer discipline. In thermal energy engineering and therefore, throughout the heat transfer course, there are two main types of problems: design problems and performance calculation problems. In a design problem, we calculate the dimensions that an equipment must have to fulfill design parameters. For example, the dimensions needed for a heat exchanger to transfer 1000 watts from a hot fluid to a cold fluid. In a performance calculation problem, we know the geometry and size of an equipment and we calculate performance such as the thermal power or the fluid outlet temperature. This is the kind of problem solved by simulators.
Application to space heating. To calculate the amount of biomass needed in the heater to maintain the inlet temperature at 23 degrees Celsius when the outside temperature is -5 degrees Celsius, it is necessary to calculate the heat losses through the walls, roof, and floor of the heater. Also the heat lost in the chimney. In this new example, it is a hybrid system with solar panels and a backup heater. Solar collectors receive heat by radiation from the sun. The surfaces of the collector are heated and transfer heat to the fluid that circulates inside them. The hot fluid goes to a storage tank where it heats the stored water. The hot water circulates in a closed circuit for heating. Hot water from the storage tank heats the surfaces of the heater. In the storage tank, a heat exchanger allows the water from the network to be heated to produce domestic hot water, or DHW. Heat recovery. In industrial processes, it is necessary to transfer heat between fluids at different temperatures. Heat exchangers of many types fulfill this function. Heat exchangers in which the fluids do not change phase are known as recuperative heat exchangers. Networks of heat exchangers. In the chemical industry, for example, networks of heat exchangers are installed in order to achieve an energy optimization of the process. Heat and steam generation. Another industrial application is the generation of heat and steam. Steam is generated in a boiler, which can be of many types. Steam can be used as energy carrier fluid or to generate electricity in a Rankine cycle. Equipment for cooling. For an electronic chip, for instance, the electrical energy consumed by electronic equipment is degraded inside it to thermal energy. This phenomenon causes equipment to heat up and require cooling to keep its temperature below design specifications. A heatsink with fins can be attached to improve the chip cooling. An additional fan can further improve chip cooling. Cooling systems with heat exchangers are also needed for internal combustion engines. Air conditioning and refrigeration need a thermodynamical cycle. Here, heat exchangers play a fundamental role with heat exchange between two fluids through the wall of the ducts. Electricity generation.
The figure shows the schematic of a combined cycle power plant. A set of heat exchangers allows generating electricity with high efficiency. In all of these applications, remember that to solve heat transfer problems you must apply the energy conservation equation and the rate equations. Don't miss the video about heat transfer mechanisms.